Today, the speaker is Dr. Sungjay. Let me briefly introduce him. Sungjay obtained PhD in 2008 at Seoul National University, and after that he did postdocs in KIAS, Korea, and Cambridge University Dump in UK, and now he is at Chicago. And he's an expert in the area of supersymmetric gauge theories in various dimensions. And today, in this lecture and one more lecture in the afternoon, he's going to tell us about new exact results in Calabi-Yau, D-branes, and complex. So let's welcome Dr. Sungjay.
Thank you. I'd like to begin by thanking all of the organizers for this wonderful workshop. I really enjoyed this fantastic talk over the last couple of days. I also enjoyed the food a lot. And although I don't have enough time to visit or look around the city itself, but also I'm very happy about this warm weather here, given this horrible and cold weather in Chicago. Anyway, so today I'm going to talk about some new exact result in Calabi-Yau space, D-branes, and readable plane. I know this title sounds a little vague. The more precise way to put the title is some new exact result in two-dimensional supersymmetric theories and their applications. So this is what I want to talk today. Okay. And before this workshop, I was asked by some of the organizers that I need to prepare this talk as a pedagogical lectures, either pedagogical lectures or research seminars. And I decided to make this seminar, this talk, somewhere between these pedagogicals and research seminars. And please feel free to interrupt me anytime whenever you have questions. Okay, so let me just start from the general introduction. In modern theoretical physics, there are many intriguing strongly coupled phenomena, both in quantum field theories and string theories. And one of the most prominent example of such strongly coupled phenomena is for confinement in QCD, of course. But I think another important example of this strongly coupled phenomena is this M theory, which has been proposed as a unified framework to study quantum gravity, where the consistent string theory can arise in a certain limit. However, this M theory is inherently strongly interacting, and nobody knows how to attack this problem, how to study this M theory in a systematic manner. These strong interactions are also very important for many condensed matter systems. Yeah, such as the non-Fermi liquid and high-density superconductors in many other systems in this condensed matter theories. However, these strongly coupled systems are far beyond the perturbative regime. Therefore, we need to develop a new and imaginative technique or tool to study this strongly coupled system in a systematic way. While in theoretical physics, basically we have three different methods to attack these strong coupling problems. One is dualities, and the other is supersymmetries, and finally we have integrabilities. In dualities, as many of you know, this gauge gravity duality, which is also known as the holographic principle, has led to a number of novel predictions on various strongly coupled dynamic systems by studying some classical Einstein gravities. But sometimes, the fascinating details of these strong interactions underlying this outcome, these predictions, still remain inaccessible. And I think any attack on this strong coupling problem is likely to require the complementary strategies, and supersymmetries has been very useful to attack this strong coupling problem. And as I will tell you in a second, in the last couple of years, we made a remarkable progress in studying the strongly coupled system, at least for the supersymmetric theories, analytically. Finally, this integrability is so beautiful and so powerful to study this strong coupling problem. The only problem with this integrability is that the example of such integrable system in the quantum field theory is really rare. And today, I'm just focused on this supersymmetric series. Well, already back in 80s and 90s.
I think it's roughly against your shirt. It's probably somewhere
Somewhere different? Is it here? Maybe it doesn't work. This one? It's okay? All right. I don't know.
Maybe put the microphone outside.
I mean, it's but okay. Yeah. Anyway, let me start. So back in the 80s and 90s, people already found some observables in the supersymmetric theory, which can be exactly computable. But somehow, most of these observables are relevant to the mathematical interest rather than the physics, like the topological invariant. But of course, sometimes they also gave us some partial information about the supersymmetric vacuum structure and the physics of the vacuum of the supersymmetric series. So one of the big questions in this community is whether or not we can find new observables in the supersymmetric theories which can be exactly computable no matter how strong the interactions are, and which also has a wide application to any supersymmetric theory in various dimensions, but which has a relevance to the physics rather than the mathematical interest, sometimes beyond the vacuum dynamics. And as I would tell you, recently, using the supersymmetric localization technique, we made a remarkable progress along this direction. So let me first briefly remind you what the SUSY localization technique is. Well, actually, I heard from Heng Yu then, Kazuo Usomichi already gave us several lectures here on the SUSY localization technique for the last couple of months. And so that many of the grad students are well educated and have a great background to understand what I'm trying to say today. So I will skip all the gory details and subtleties about the SUSY localization technique. I just want to give you some brief idea what the SUSY localization technique is. So let me consider this following path integral, where this S is the action of the theory, what we'd like to understand. And suppose that this action is invariant under the SUSY transformations generated by the supercharged Q. And the supercharged Q satisfies these relations where J is a generator of a certain bosonic symmetry, the original theory S. Then let's now add to this theory to the following Q exact deformations with some parameter T, and do the path integral again. And this partition function, in principle, is a function of this parameter T. However, if the term V appears here, is invariant under this bosonic symmetry J, one can show that this partition function is actually independent of this parameter T, which implies that this partition function at T equal to 0 is the same as the partition function at T equal to infinities. And this is very nice because on the left-hand side, we have an original theory whose dynamics is governed by this action, S, is fully interacting and quantum. So in general, yes?
Yeah, that's probably better this one. Since you don't need to write black or white.
Yes. Sorry. Okay. So in general, it's very difficult to evaluate the path integral of these theories. However, on the right-hand side, we have a different theory, whose dynamics is governed by this deformed action rather than the original action. And the limit where this parameter T goes to infinities, this deformed theory is in the semi-classical regime. Therefore, we can easily evaluate the path integral of these deformed theories in the semi-classical regime by performing the Gaussian integral. In other words, we can just do the WKB approximations, and in the limit where T goes to infinities, this WKB approximation becomes exact. So as a consequence, this partition function of the original theory can be written as the following simple form, where phi star represents the set point configurations which can minimize this deformed action rather than these original actions. And to contribute to the path integral, the set point configuration has to be supersymmetric. This is because otherwise, and suppose that the set point configuration is not supersymmetric, then eventually we have some fermionic zero mode. Therefore, their contribution to the path integral will be trivial. So phi star are the supersymmetric set point configurations. Then we have a classical action contribution and the one-determinant contribution around each of the supersymmetric set point configurations. And this is an exact answer. We can use the same argument to evaluate the correlation function of the BPS operator, where this BPS operator is an operator that is annihilated by the supercharged field. And using the same argument, we can show that this correlation function of this BPS operator can be written as the following form, and this is the exact answer N. Well, the supersymmetric localization technique, this idea itself is nothing new. I mean, people already studied this back in early 90s and 80s. Then some of you may wonder what's the difference between the old achievement using the SUSY localization technique and the recent achievement. Well, in 80s and 90s, people would like to find the constant spinors which satisfy these equations, and the associated supercharges satisfy these nilpotency conditions. However, in many cases, like especially the theory defined in the curve manifold, you have to do so-called topological twisting to find such a nice constant spinors and these nilpotent supercharges. However, this topological twisting essentially projects this full physical Hilbert space down to very tiny subspace, which is called the topological Hilbert space, more or less the same as the supersymmetric vacuum space. And that explains why this exact observables what people computed in the 80s and 90s barely knows about the vacuum physics of the given supersymmetric theories. In many cases, they are relevant to the mathematics, but doesn't tell us much about the physics. Of course, there are some exceptions too. But anyway, so recently, people would like to find some killing spinors which satisfy these equations rather than this constant spinor equation. And the associated supercharges usually satisfy these relations where J is a certain bosonic symmetry of the series. It's not important. And the most important thing here is that there are some observables in the supersymmetric theories where you don't need to do any topological twisting to find the scaling spinors and these nice supercharges. And because of that, the physical Hilbert space doesn't need to be projected down to this topological Hilbert space. Therefore, it is quite natural to expect that this new observable in the supersymmetric theory may tell us about something new, something relevant to the physics, sometimes beyond the vacuum dynamics, rather than the mathematical interest. Okay. And so what are these observables? Well, as many of you know at the moment, so these observables are 4-sphere partition functions and 3-sphere partition functions. And so superconformal indices in this 3 dimensions and 4 dimensions developed by these people. And using this new exact result, in the last couple of years, we made a remarkable progress in understanding the strong dynamics of the supersymmetric series in these dimensions. For instance, we learned about this Alday-Gayato-Tachikawa correspondence, which relate the 4-sphere partition functions of 4D n equal 2 supersymmetric gauge theory to Liouville and Toda correlation functions. We also learned about the F theorem, which was also discussed by Nishioka-san, which is a kind of 3-dimensional counterpart of the Jamolodchikov-Z theorem in 3 dimensions. From this exact 3-sphere partition function of the supersymmetric series. And using this new exact result, we can also perform the precision test of various conjecture dualities and relation between the duality in different dimensions and so on and so forth. So it's quite natural to keep pursuing the similar inquiry down in the 2 dimensions, such as 2-sphere partition functions, hemisphere partition functions, and real projected 2-plane partition function. And finally, this elliptic genus, which developed by these people. And this is the things what I want to discuss today. And using this new exact result, I will attack some basic and interesting problems in the two-dimensional supersymmetric theories in relation to the string theory compactified in the Calabi-Yau manifold, which still remains some challenges. So this is the end of the general introductions. Any questions so far? Okay. So today, is there any? So in this morning talk, I mainly focus on these two-sphere partition functions. I will discuss how to define such a theory in the two spheres, and how to compute the two-sphere partition function exactly using this localization technique. Then I will discuss some properties of the two-sphere partition function, analytic properties, this kind of thing, and also we'll discuss about this regularization scheme dependence on this two-sphere partition function. And then I will move on to some application of this exact result, such as investigation of the mirror symmetries and the quantum phase of the gauge linear sigma model, and this kind of thing this morning. It's more like the pedagogical lectures. But in the afternoon, I will discuss about another application of this new exact result, two-sphere partition function, which is to compute the Walsh instant correction to the jamological metric. Then I will discuss about different new exact result in the two-dimensional theory, such as hemisphere partition function and RP2 partition function. Then I will discuss about some issues on the D-brane charges and reinterval charges, and we'll resolve the puzzle and solve the puzzles using this new exact result, the hemisphere partition function and RP2 partition functions. So in this morning talk, let me first talk about the supersymmetric theories on the two spheres. First, we can show that this two-sphere partition function on this, the supersymmetric algebra on the two sphere is given by this SU2/1, which is a subalgebra of this n equal 2,2 superconformal algebra. This SU2/1 contains two bosonic subgroups, which is a SU2 and a U1, which can be understood as a rotational symmetry of the two spheres, and this U1 represents the vector U1R symmetry of this 2,2 supersymmetric theories. However, this axial U1R symmetries of this 2,2 supersymmetry is now explicitly broken on the two spheres unless the given theory preserves the conformal symmetry from the beginning. Actually, we can embed this SU2/1 super algebra inside this 2,2 superconformal algebra a little differently, so that the conserved U1R symmetry can be identified as an actual U1R symmetry rather than vector U1R symmetries. In that case, this vector U1R symmetry is now explicitly broken, again, unless the given theory preserves the conformal symmetries from the beginning. But today, let me just focus on this SU2/1, where U1 can be identified as vector U1R symmetries. This SU2/1 supersymmetry on the two sphere can be parameterized by these two killing spinors, epsilon and epsilon bar, which satisfy these killing spinor equations, where L denotes the radius of the two spheres. One can show that each of these killing spinor equations has two independent solutions. So we have four independent solutions in total, which can parameterize these four supercharges on these two spheres. So this is the supersymmetric algebra on the two sphere.
Sorry, just you said it, but it's the algebra whether or not the theory is conformal?
Yes. Right, then we have to find this SU2/1 representations on the various supermultiplets, such as chiral multiplet, vector multiplet, and the twisted chiral multiplet. And then we also need to construct the supersymmetric Lagrangian on the two sphere, which is invariant under this SU2/1 transformation. Well, in general, when you try to couple the given quantum field theory to a curved background, curved manifold, there are some ambiguities in adding some correction terms which are suppressed by, say, suppressed by this radius of these two spheres, which will disappear when you take the flat space limit. However, by demanding the theory to preserve this SU2/1 supersymmetries, one can unambiguously determine such a correction terms by using, either the offset supergravity formalism developed by this Festuccia and Cybers and Komagatsky and many others, or just tedious iterative method. In other words, just adding this 1/L corrections in the SUSY transformation rules and supersymmetric Lagrangians and see whether it gives you something consistent. If not, then just add 1/L square correction to the theory, to this transformation rule and the Lagrangian, and see again whether it gives you something consistent. Then either way, at the end, one can show that in this SUSY transformation rules, there are only 1/L corrections, but in the supersymmetric Lagrangian, there are up to 1/L square corrections. For instance, we can see this 1/L corrections in the SUSY transformation rules for the gauge-no field in the vector multiplet. And we can see this 1/L corrections and 1/L square correction here in the kinetic Lagrangian for the vector multiplet. So we have a kinetic Lagrangians on these two spheres. Then what about the supersymmetric interactions? So let me first talk about the superpotential terms. So here we found that in order to introduce such a superpotential term on the two spheres, the vector U1R charge of the superpotential has to be given by 2. This is because the supersymmetric algebra SU2/1 on this two sphere already contains this conserved vector U1R symmetries. And that explains why the superpotential need to carry 2 vector U1R symmetries. And the superpotential term on this two sphere is given by this expression, more or less the same as the term in the flat space. However, we can introduce arbitrary form of this twisted superpotential, which is a function of the twisted chiral multiplet. And this twisted superpotential on the two spheres is given by these expressions, where we have this 1/L corrections. This is very important. And one of the examples of this twisted superpotential is this Fayette-Illopoulos couplings and the two-dimensional topological couplings, where the theta is a two-dimensional theta impulse. This is one of the examples of these twisted superpotentials. So we have some supersymmetric theories on these two spheres. And from now, I will evaluate the path integral of this supersymmetric theory on the two sphere exactly using the localization technique. So any questions so far? All right, so let me first remind you how the SUSY localization technique procedure usually goes.
So the original motivation is really as a tool to calculate those exact superpotential.
Sorry, what?
The original motivation on putting these things on a sphere was that?
Because we want to introduce some interacting theory to the theory, interacting theory on the two spheres.
I see.
Otherwise, we cannot.
Superpotential for 2,2 was already computed by Witten many years ago.
What kind of observables?
By twisted superpotential, by integrating out all the chiral fields.
Effective twisted superpotential. Yeah, on the Coulomb branch. Yes.
Okay. Oh, I see.
This is just a classical Lagrangian,
Okay.
supersymmetric Lagrangian on the two sphere. We need to ask the following question: whether or not we can introduce the interaction of the two spheres, and the answer is yes, and the interaction term is given by this expression. Just classical construction of the classical Lagrangian of the two spheres.
One question.
Mm-hmm.
You can put supersymmetry on S2 and
Mhm.
some correction.
Yes.
1/L term, right?
Yes.
But does it imply that you can also put supersymmetry on two-dimensional digital space?
By analytic continuation, yes. But it contains some non-unitary terms in many cases. Okay, so we first need to choose a supercharged cube to do this localization technique, and then we need to find a good Q-exact deformation so that the path integral can be localized onto simple enough set of point configurations. And then we need to compute the one determinant around the supersymmetric set of point configurations. So let's do it for this two-sphere partition function. So we choose a particular supercharged Q in this SU2/1 supersymmetry algebra, which satisfies this relation, where J generates some rotation on the two spheres, like in this figure, having two fixed points at north and south pole, and R represents the conserved vector U and R symmetries. So given this choice of supercharge, one can show that the kinetic Lagrangian for the vector multiplet, chiral multiplet, and the twisted chiral multiplet, and even superpotential terms are all Q-exact. And from this fact, we can obtain a sort of decoupling theorem, which is the two-sphere partition functions has to be independent of the gauge coupling constant. This is because the kinetic Lagrangian for the vector multiplet is Q-exact. And this two-sphere partition function has to be independent of the complex parameter in the superpotential. This is because the superpotential is also Q-exact. And from this fact, especially this independence of the gauge coupling constant, this fact guarantees that the two-sphere partition function of the supersymmetric gauge theory, having IR fixed point, actually compute the two-sphere partition function of that CFT at IR fixed point.
If I just start with a general CFT, is there a unambiguous way to define a two-sphere partition function?
Yes. By conformal mapping.
Don't you get just one? I mean, how do you fix a normalization? I mean, I
didn't mean there's a normalization issue.
No, I just don't understand how you fix normalization. I guess I understand if you have a moduli space, then you can kind of, there's a meaningful way to say what the two-sphere partition function is. But without referring to deformations of the theory, how do you, I mean, if you start with Pavnikov, then yes, but if you start with the abstract conformal field theory, given some vertex algebra and spectrum operators, I mean, is it meaningful to say what the two-sphere partition function is? How is that defined?
Without this dependence on this marginal coupling constant?
I mean, is it only meaningful through dependence on marginal coupling? I suppose
Yes.
that's...
Yeah,
okay.
that's the answer.
I see.
Otherwise, it's a number.
Yeah.
Okay.
So is the answer going to depend on the radius of the two-sphere?
This one? No. There is some factor that depends on this radius, but I will come to that one later. It's related to this central charge.
Liu.
This is conformal.
Yeah.
Where are you? Okay, so I will choose this Q-exact, this kinetic Lagrangian for vector chiral twisted chiral multiplet as our Q-exact deformation. Then we need to work out the supersymmetric zero point configurations where this pattern theorem can be localized into. Well, this analysis actually depends on model by model. So let me first discuss about the supersymmetric gauge theory in 2 dimensions, which is often called the gauge linear sigma model. Here this gauge group is arbitrarily, and this gauge theory is coupled to the chiral multiplet in any representation R, and this the U and R charges of this chiral multiplet is given by Q. In this case, we can easily show that the supersymmetric zero point configurations can be described by the set of equations. The sigma 2 is one of the real scalar field in the vector multiplet, which can have some arbitrarily constant value on the two spheres. And the other real scalar field in the vector multiplet, sigma 1, should satisfy these equations, where this flux on the two sphere is properly quantized. Sometimes it's called the GNO quantized. And these two scalar fields in the vector multiplet has to commute to each other. And all other fields in the theory must vanish. So this is the supersymmetric zero point configuration. And the next step we have to do is to compute the one-to term around this supersymmetric zero point configuration. So for simplicity, let's
Sorry, was sigma 1 also constant?
sigma 1 is a quantized number because the
No, but you say this is both f1 and sigma 1 constants. Take some constant value.
when you integrate over two spheres, yes.
But themselves.
It's some function on the two spheres.
The zero point conversion is the sigma 1 does not is not constant by
it's
itself.
a constant on two spheres. Yeah, you can make such a gauge choice such that the sigma 1 is constant. That's okay.
And this saddle point is only for specific deformation term you introduce.
Yes.
Right.
The zero point